where do you think ECoG can go? Where do you think we could push clinical ECoG grids?
I think I'm going to sort of dodge that a little bit and just say that there's a lot of really exciting ECoG data coming out. And there are lots of things you could point at, but one that's got a lot of press and really is pretty cool is the work out of Eddie Chang's lab at UCSF, former colleague of mine at UCSF, showing that you can get some rudimentary, to be fair, but some decoding of speech from ECoG. What you're doing is you're actually decoding the speech motor signal. So it's motor decode in the same way that sort of motor BCI is, but it's on the speech side. And I think that the precision that they're able to get isn't what you would want for an everyday prosthesis that you could sell easily in market. But I also think that what they're getting is better than a lot of people would have thought you could get a few years back. And so that's just one example, but I think there are lots of it. It's a really exciting time for thinking about new ways of interfacing with the brain.
Yeah, we've done some high resolution ECoG work, and based on some of the Bujaki papers that we had all read, thinking about the kind of propagation of signals through cortical tissue, we didn't expect that placing electrodes, 50 microns away from each other would yield any new information. But I'm starting to be convinced that there's more there than people are picking up.
Yeah, and you guys, I believe, have the record now. What is it? I don't know how many you actually record at the same time, but it was around 30K, right?
Yeah, it's 30K. Yeah.
Yeah, so that's pretty impressive.
Cool. Yeah, it's pretty neat. I was ECoG skeptical, but when we started doing these recordings, it opened my eyes a little bit. I mean, it's still law of diminishing returns. I would much rather have 30,000 spiking channels than 30,000 ECoG channels. But
fair enough.
Yeah. Yeah, I mean, I think so I agree with what you said. I think it's surprisingly good. I also think some of the human stuff has sort of discovered this interesting zoology of units that are living on the top of the cortex.
Well, what do we think that is? Do we think those are axons?
Yeah, that's what I was I think they're layer 1 neurons, right? There's enough neurons on there. You're not necessarily getting a spike on every channel. So an undergrad in my lab actually did a model of this, and there's just no way you're getting a somatic spike from a millimeter away. Yeah, you need new physics.
It's not clear if there's some weird ectopic layer 1 cell that's hanging out and you can record a spike from, whether that's decodable or not.
But there's neurons up there. We sort of, we did our own histology for that just to check. And it's like Christmas lights. There's neurons up there, right? The epilepsy people study those neurons all the time. So I think it's probably just layer 1 neurons, right? And what that would also mean is you got to stay close, right? So if you start, if you develop a layer of scar tissue, I'm curious if you have a solution for that, because once you're 50 microns away, that's going to be a problem, right? Yeah.
Yeah, no, that's, from a clinical standpoint, that's not where we're going. We're not building high density ECoG grids. We had an opportunity to leverage the Argo to collect some of that data, but we're going for penetrating microelectrodes.
Penetrating, cool, yeah. 1 over R is just really hard to get around, so.
That's true.
Or R squared or R cubed.
Usually with neurons, it's 1 over R, I would argue. Because, the R squared, you have to be a millimeter away before it starts really being like a dipole.